Okay, I think we can start. Colleagues from everywhere, Egypt, Morocco, Greece, Peru, Japan, China. So, okay, hello everyone. On behalf of the IOMP, I'd like to welcome all of you to the International Medical Physics Week webinars organized by the IOMP School. IOMP represents about 25,000 medical physicists worldwide, working in all areas of medical physics. The webinar yesterday was on X-ray imaging, principles of CT dosimetry, image quality. Today and tomorrow, we'll focus on radiation therapy. Our speaker today, Dr. Lorenzo Brualla, is an excellent colleague working in the field of proton therapy. But first, it's my great pleasure to introduce today's moderator, Professor Eva Bezak.
Good evening, everyone.
Eva lives in Adelaide, Australia, and works in the University of South Australia. She's also the Secretary General of the IOMP. So, Eva, the stage is yours.
Thank you. Can everyone see the screen?
Yeah.
Yeah, wonderful. Good evening, everyone. And it's an absolute pleasure to be here. And to a degree, I'll be a bit cheeky. It's right that I am chairing this session because I am from Adelaide. And today's topic is on proton therapy. And Bragg Peak was discovered by Sir William Henry Bragg here in Adelaide in Australia at the beginning of the last century. You all know that protons and heavy ion particles are considered to be ideal particles for use in external beam radiotherapy due to their superior properties of dose distribution that results in higher and more conformal dose to the tumor, while the dose to the healthy tissues is much less as compared to the traditional X-ray radiation produced by Linux. And we have seen all around the world rapid establishment of new proton facilities in the last decade or more, all around all countries. But things are never simple. We all understand that accurate radiation delivery is a must. However, several factors contribute to the overall accuracy of treatment, including algorithms used for determination of ionization chamber quality factors and for computation of absorbed dose distributions in patients. In this context, Monte Carlo methods are considered to be the state of the art. In this webinar that I am welcoming you to participate in, an overview of the current status on determination of ionization chamber quality factors in proton therapy will be given. Current efforts being developed in this field will be presented, in particular the benchmarking process of the newly developed extension for proton simulation within Monte Carlo General Purpose Radiation Transport Code, Penelope. Our esteemed speaker tonight is Dr. Lorenzo Brualla, who is a privat docent of experimental radiation oncology at the Faculty of Medicine of the University of Duisburg-Essen in Germany. He is also a researcher at the West German Proton Therapy Center of Essen. He obtained his PhD in physics at the Technical University of Catalonia in Spain. His research activities are related with the Monte Carlo simulation of radiotherapy and dosimetry problems, both with conventional as well as with proton therapy. He is the author of the freely distributed Monte Carlo dose verification system PRIMO for simulation of medical linear accelerators and absorbed dose distribution in patients. Without much more talking, I will hand over to Lorenzo. I would like to ask you to type your questions into chat, and following Lorenzo's presentations, I will be moderating the discussion. That means that I will be reading your questions to Lorenzo. Thank you and enjoy the evening. Lorenzo, you can start sharing.
Thank you, Eva, for this very nice introduction, and also thanks to John for inviting me to this webinar. It's a great pleasure to be here. So let me first make sure that is everybody seeing the screen? Okay, great. Yeah. So thanks for the introduction, and you, Eva, precisely nailed down the point of proton therapy, which is the very nice absorbed dose distributions that you can get. However, this comes at a price, which is that we need to increase the accuracy of our dosimetry. And this is the main topic of this webinar. The webinar is divided first in an introduction to proton therapy, very briefly. Then we will go through an introduction to Monte Carlo methods in radiotherapy, not only proton therapy in general. And then we will move to see which are the pitfalls that can occur during Monte Carlo simulation of dosimetry problems in proton therapy. And we will see 3 examples of current research problems in which we are working in dosimetry using Monte Carlo simulation. So this is the pretty much the same plot that you showed, Eva, which shows the Bragg peak. Protons, as they enter into water, deposit dose. And the deposited dose, it is more or less constant throughout the beginning of the slowing down process of the proton until a large amount of dose is delivered, and at the distal end of the delivery of the dose, there is virtually no dose delivered. This is the nice characteristic that we shall exploit in proton therapy, the fact that behind the Bragg peak, there is no dose distribution. So to compare with the typical absorbed dose, depth dose distribution that one obtains in photon therapy, in conventional X-ray therapy, we see that photons behave like this. We have here a build-up region, then we have a maximum dose at the very beginning of the entrance, and then we have a slow decaying tail, in contrast with protons. However, our tumor is usually thicker than the thickness of this Bragg peak, so we need to produce what is called the spread out Bragg peak, which is the addition of several Bragg peaks, each obtained with different energies, that all of them add up to this dose distribution. So this is the SOBP, the spread out Bragg peak, which is typically used in proton therapy treatment. This is the typical comparison that you can see between proton therapy on the right hand and conventional photon therapy on the left hand. With photon therapy, you usually get a dose, low dose bath around the planned target volume, which is not the case in proton therapy. So the objectives of proton therapy are it allows dose escalation, increase the dose. That is when one wants to improve tumor control by delivering a larger dose with respect to conventional radiotherapy, or it allows to spare normal tissue, therefore reducing adverse events and reducing also the irradiated volume, which in turn reduces the radiation-induced secondary malignancies. So proton therapy is particularly convenient in case where very high doses are needed, very sensitive patients or structures are involved, or very large irradiated volumes are involved. This translates into the following clinical targets. Here I'm just naming just a few, just as examples. Case of very high doses like chordomas, or chondrosarcomas, or prostate cancer, where you need, these are very radiosensitive tumors that they need very high doses. Very sensitive tissue or very sensitive patients. We are talking here in the case of sensitive tissue irradiation of eye tumors. In the case of sensitive patients, we are talking about pediatric patients. And this is particularly relevant for us at the West German Proton Therapy Center, where 80% of our patients are children. Or when very large volumes need to be irradiated, for instance, in the case of craniospinal irradiation. This is to show you which are the percentage of sites irradiated at the West German Proton Therapy Center. Most of them are head and neck, that coincides with children, and few more spinal irradiations. This adds nearly to 80% of our irradiations. Very few words about the beam delivery techniques, because we will need that in order to understand why we are solving the kind of problems that we will show later. Beam delivery traditionally was done using single scattering or double scattering techniques without entering into details. That means that we have a pencil beam, proton beam, that is spread using either single scattering or double scattering, and then it is conformed using apertures, blocks of material to limit the shape of the tumor. And then we have uniform scanning, which is something in between double scattering and pencil beam scanning. That is, there is a movement of the pencil beam, and the last developed technique is pencil beam scanning, which is similar to what we know from old CRT TVs. You have a pencil beam of ionized matter, electrically charged particles, which are protons, and you can direct this beam with two pairs of magnets. So you can paint the tumor without any need of scattering. This pencil beam scanning technique is the one that is currently installed in most centers, and the other techniques still, although they are still in use, they are not longer installed, at least not massively installed as in contrast to pencil beam scanning. So let's say we have essentially two ways of doing the beam delivery. One is putting material layers in front of the pencil beam and scattering, producing a scattering, and the other is just directing the pencil beam. So entering into Monte Carlo codes for radiation transport, there is a wealth of widely distributed Monte Carlo codes. It is common that people talk about, I did that with Monte Carlo simulation, I obtained these results with Monte Carlo, but these sentences usually mean little more than I just used some random numbers to obtain my results. There are many Monte Carlo codes, and depending on the Monte Carlo codes and how they are applied, that will derive into the accuracy of the results that I am obtaining. So codes can be classified as general purpose. General purpose codes are those that, general purpose radiation transport Monte Carlo codes are those that cover a wide range of energy from about 1 kilo electron volt up to 1 gig electron volt. They can simulate any material in arbitrarily complex geometries. And examples of these codes are GN4, MCNP, FLUCA, All these three codes, they deal with electrons, photons, as well as protons, neutrons, and other type of particles. And then we have Penelope and EGS NRC, which typically they only deal with photons and electrons and positrons. No, not with protons, which is what we are interested in. However, there is a recent development regarding Penelope, which now includes protons, and protons can be simulated, and we will talk about that later. Then we have fast Monte Carlo codes, which they are limited in the energies that they can simulate, so therefore they can only simulate energies within the clinical interest, which is around or of the order of mega electron volts. They only simulate, or usually only simulate low Z materials, that is those typical in the human body. Typically in bint geometries, those that we find when we simulate computerized tomographies. And examples of these codes are DPM, XBMC, BMC, ray station. The three of them in this list, they only simulate photons and electrons. Ray station simulates protons. And then there is another type of Monte Carlo codes, which are those called pre-computed Monte Carlo, in which during simulation time, Monte Carlo simulations are not conducted, only lookup tables are visited, and these lookup tables were built using a general purpose Monte Carlo simulation. So, as we gain in speed, we lose in accuracy. The main problem that limits Monte Carlo, general purpose Monte Carlo codes is the simulation time required. Very briefly, let's go through how a Monte Carlo simulation of radiation transport works. We have a particle entering into the boundary of a material layer. We'll call it material 1. And we sort the step lengths that this particle will travel using a random number. When we decide where an interaction will occur using a random number, we sample which type of interaction will occur. In this example, we only have two types of interactions type A or B. And also using another random number, we decide which kind of interaction occurs. And then using the interaction cross-sections of the particular interaction that was sampled, we decide how much is the energy loss, how much is the change of flying direction, and if any secondary particles are produced. And then we continue the simulation until we arrive to a boundary with a next material. We stop the particle at the boundary, we recalculate our step length, and we move the particle with the new step length in the new material. So to see how this translates into a code, this is a very simple Monte Carlo code. You see, Monte Carlo codes not necessarily have to be very complex. Actually, they are quite simple. What it makes them complex is that we put lots of blocks, simple blocks together. First, we define a source. In this case, our source is a source pointing upwards, and we are simulating a low energy neutron source. All neutrons are pointing upwards, and they are emitted in a pencil beam fashion. Then, as I showed in the previous slide, we sample the flight distance. Here we have our random number. And then we sample the type of interaction. This is an isotropic interaction. And in all these places, we have randomness introduced. How this works, we have here a video. What we are sampling is, you will see it right now, is the number of interactions that occur at a given distance from the source. So as you see, very few particles have their first interaction just after being emitted. Very few particles can travel freely a very long distance, and most of the particles have interactions in the mid-range. If we run the simulation long enough, we get this nice plot, and this is the distribution of interactions according to the distance from the source. So here it comes several things into the discussion that all Monte Carlo codes share in common. In all Monte Carlo codes, we are tallying a quantity. Therefore, we need to compute the expected value of that quantity. And the expected value is computed by taking averages of the quantity of interest. The quantity of interest can be the energy, can be the fluence, can be any quantity that we are interested in. The way to do it is that we run many simulations of many primary histories, that is many primary particles. And for each primary history, we compute the quantity of interest, and then we accumulate this value in a tally. And at the end, we take the average. Every expected quantity in a Monte Carlo simulation comes associated with a variance, with a standard deviation, because what we are doing is we are computing a stochastic, we are doing a stochastic calculation. This is a plot to show you how to correctly interpret Monte Carlo results. Here we have a typical dose distribution from photons in this case, but to the matter of the discussion, it doesn't, to the objective of the discussion, it doesn't matter whether it is photons, protons, or whatever. And we are comparing our simulated results, which are the dots, with the, sorry, which is the histogram, the simulated results, we are comparing with the experiment. Each histogram, each bar of the histogram of the simulation has an uncertainty bar, and this is very important. Every Monte Carlo quantity, every Monte Carlo tallied quantity must come accompanied by a statistical uncertainty. So, if I tell you that these uncertainty bars are given to a coverage factor k equal to 1, that is, we are plotting to 1 standard deviation, then 68% of our results should coincide within the statistical uncertainty with the experiment. That means that if 68 must coincide, 32% must not coincide. So if I am telling you that this plot is given to k equal 1, you can immediately say that I am lying to you, that these results are fake, because it's impossible that all beings coincide with the expected experiment with a coverage factor equal to 1. However, if I am telling you that these uncertainty bars are plotted to k equal to 2, that is 2 standard deviations, then 95% of the results will coincide, 5% will not coincide. Okay, here there are not so many points, so it is quite probable that all of them are coinciding with the experimental data. So that is why it is very important to give the Monte Carlo tallied quantities associated with a statistical uncertainty and indicate the number of standard deviations that we are using to indicate the statistical uncertainty. As I said, the main problem of Monte Carlo simulations is the exceedingly long simulation times required to obtain reasonable results. The reason is rooted to this fact, it is because the uncertainty goes with the square root of the number of simulated histories. So if we want to reduce the statistical uncertainty by a factor of 2, we need to increase the number of simulated histories by a factor of 4. And here you have an example of isodose lines of an electron irradiation of a conjunctival lymphoma. And on the lower right end of the image, you see the number of simulated histories. So in order to get more or less decent isodose lines, you see we needed 200 million simulated histories. Well, what we had at the beginning, 1 million simulated histories, gave us this horrible plot. So that's another caveat. When you see very smooth lines in isodose lines, or very smooth plots in general in Monte Carlo, take them with a pinch of salt. It's many times it occurs that some smoothing or ironing or some other algorithms have been applied. And of course, when you apply these kind of algorithms, then all traces of a statistical uncertainty are lost. The solution to reduce a statistical uncertainty is by means of the so-called variance reduction techniques. And variance reduction techniques are aimed at improving the simulation efficiency. Beware, they are aimed at improving the simulation efficiency, not at reducing or not necessarily at reducing the simulation time. There are some variance reduction techniques that might increase the simulation time, nevertheless produce a more efficient simulation. Also, the field of variance reduction techniques is a field that is, let's say, maybe a little bit of art, or more an art than a science, because variance reduction techniques, if not properly applied, they can produce either biased results or produce simulations that are less efficient than not applying the variance reduction techniques. So with all these elements from a Monte Carlo simulation, we can now figure out which are the ingredients of a Monte Carlo simulation of radiation transport. We have first to define a primary source, the source of our primary particles. We need to define a geometry file, that is the world in which our particles will travel. We need to define the material files, that is the description of the materials composing each element, each body of this world defined in the geometry file. We need to define the transport parameters, which is how are we going to transport the particles inside the geometry, which will be our absorption energies and so on. We will go into more detail afterwards. We need to define variance reduction techniques that we will apply. And we need to define also the tallies. That is, which quantities do we want to score at the end. Knowing that, we will see some of the dosimetry problems that I mentioned to you at the very beginning. The problems that we will deal are first, the Monte Carlo simulation of single pencil beams, then Monte Carlo simulation of multiple Coulomb scattering of protons, and finally, Monte Carlo simulation of beam quality correction factors of ionization chambers. So starting with the Monte Carlo simulation of a single pencil beam, this is a work that we have recently submitted. And in order to evaluate this new Proton module for Penelope. This Proton module is called PenH, and we wanted to benchmark this Proton module for Penelope with existing codes, mainly GN4, which is widely used in this field, and also with experimental data. Our experiment consisted on the following. What we have is a water tank, and we have a single pencil beam from our facility impinging on this water phantom. And then we score the dose using a matrix detector, which we can score simultaneously with 1020 ionization chambers, the dose at a given depth. And we move this detector downwards so to have a 2D dose distribution at different depths. So we can know the depth dose distribution along this line, along this line, along this line, and so on. We define each of these lines according to their radial distance to the center, the beam central axis. This is a plot of a simulation we did of the problem. So this is a transverse axial image of this water phantom. Here we have the beam impinging on the water. This is the radial distance in that direction, and in that direction we have the depth. In order to make evident the gray shades, we did not plot directly the dose, but we plotted the logarithm on base 10 of the dose plus 1. So if you plot directly the dose, you just see a black line, and everything else you see it white. Okay? And according to the common practice in the field, the point at which the isodose surface at which the dose drops to 10% of the maximum dose, this line defines the core of the dose. Between the 10% isodose surface and the 0.01% isodose surface, which is this one, this region is called the halo, and outside this region is called the aura. And what we wanted to see is how our code performed in evaluating the dose respect, the depth dose distributions respect to the experiment in these three regions. What we obtained was the following. We used GN4 as our Monte Carlo code that we wanted to compare with. PNH, which is the implementation of proton transport in Penelope. There is a code called a stirping, which is also a variation of PNH, in which the nuclear models were implemented by a stirping on an original PNH that only had electromagnetic interactions. And then we also compared with our Monte Carlo treatment planning system registration. And here are the results. So for a beam of 225 MeV, the central axis, most of the codes give more or less the same result than the experiment. The experiment is plotted with the squares, okay? PNH and Topaz, which is GN4, give essentially the same quality of the results. And as we get away from the central axis, we start to observe differences, okay? I want to look particularly at this depth dose distribution, the one at 10.67 centimeters from the central axis. Here what we have is the experiment, the result obtained by JN, which is remarkably good. And here we have PNH. The difference between PNH and the results obtained by GN and the experiment all this difference is accounted to the lack of simulation of neutron transport in PNH. If we did the simulation of giant disconnecting neutrons, and we obtained exactly the same result. So PNH behaves very well, but it lacks the simulation of neutrons. If you are interested in out-of-field doses in proton therapy, which, as you can see, have a large contribution from neutrons, then you need to simulate neutrons. Same results for 160 MeV, and you see the agreement in the central axis is more or less the same than we got before. However, notice the change in the shape of the depth dose distribution by reducing by 90 MeV the beam energy. And again, the same effect because of the lack of neutrons. The treatment planning system RayStation, which has a fast Monte Carlo algorithm, remember that we commented at the very beginning of the presentation that this kind of algorithms, they did a lot of assumptions, nevertheless behaves quite well for the range in which we are interested in. Notice that here, for instance, we observe differences when we are 5 orders of magnitude below the maximum dose. So this here we are looking into micro dosimetry. And again, the same results or similar characteristics for 100 MeV. Another problem, the problem of multiple Coulomb scattering. In this case, what we are interested is we have a beam impinging, a pencil beam, proton pencil beam, impinging on a material layer. This is what why I talk at the beginning of the different beam delivery modalities that exist, several of which have to do with the fact that you put material layers on the beam path. What we want to know is if we are able to simulate the spread of the beam accurately. And we tested aluminum, brass, and you will see in the next slide, lucite, which are materials that are typically used for beam delivery. And all the codes tested, here theta naught is the experimental result, theta p is with PNH, Penelope, and theta t is GN4. And this is Molière, Fano analytical approximation. And all of these codes, an analytical model, in this case, they give very good agreement with experimental data, okay? If we go to the case of lucite, which is used in the treatment planning, which is used in our facility, and all facilities actually, again, we get the same good agreement. The only points that show disagreement is the point related to RayStation pencil beam algorithm. This is an analytic algorithm implemented in RayStation, which essentially no one uses. It is there just for the sake of completitude, nothing else. But you see, in this case, this analytic algorithm does not fit the bill. For the rest, we get very good agreement among all codes and experiments. And now let's go into an important problem in dosimetry, which is the determination of correction factors for ionization chambers. These correction factors are necessary when one is interested in using the ionization chamber that one has for really accurate dosimetry. And these ionization factors, these correction factors, the whole community is working on finding results and publishing them, because they determine to a good extent the quality of the dosimetry. This is a publication of Baumann, Horst, Zink, and Goma. They did not simulate an ionization chamber. They went to a simpler problem in preparation and to identify the source of possible differences that we will see that occur, in which they just use, instead of ionization chambers, they use volumes of air, which it is the simplest approximation to an ionization chamber. An important quality to determine these correction factors is the FQ. The FQ is obtained as the ratio of the dose computed in water in a small disk of water divided by the dose computed in air for the chamber. In this case, the chamber is just the volume of air. Okay, so here, this is the reference dose in water. This is the volume where the reference dose is studied in water, and this is the one of the volumes, air volumes, that will be used, and this is the other air volume that will be used in the comparison. And this is a quite relevant result. These points here correspond to the FQ obtained with the small cylinder that you saw in the previous slide, and this one is are the results obtained with a large cylinder. And you see that even in this very simple problem, you have discrepancies among the three codes. This is PENH, this is Fluka, and this is JN4. And okay, although Fluka is compatible within the statistical uncertainty with JN4 and PENH, PENH is not compatible with JN4. More or less the same occurs here. One could say that PENH is barely compatible with JN4. So even in this simple problem, these differences are observed. However, notice the scale. This is 1.130, 1.135, 1.140. So the percentual differences between these results are really very, very small. But this is the kind of accuracy that it is required in this kind of problems. Nothing to do with the accuracy usually required in those distributions in patients, which 2% is good enough. This is another article from Goma and Sterpin, in which they use PENH, the version of PENH in which nuclear interactions were implemented by Sterpin. And they computed this FQ, in this case, not for air cylinders, but for several ionization chambers. I am focusing on a particular model, the NE2571. And these are the results obtained for 225 MeV. Here is 150 MeV, and this is another energy. So this scale, this axis increases with the energy of the beam. So notice in this case, 150 MeV. Goma and Sterpin, they obtained this result. However, Goma and Sterpin, 3 years, no, Goma and other co-workers, sorry, obtained 3 years before with more or less the same code, is PENH, but with another nuclear interactions implementation. Actually, the nuclear interactions implementation was taken from JN4. They obtained this result. Behind the triangle, there is a square. They obtained this result. So completely different. And Wolf, using JN4, but depending on the type of physics chosen, obtain this result and this result. So you see that you obtain results that are not compatible among themselves, everyone using, actually in this case, the same author using the same code, just changing the transport, just changing the physics interaction models. And in this case, the same author, or one of the same authors, slightly changing the code. Possible reasons for this. This is the geometry of the NE2571 chamber that Goman and Sterpin used in the last paper they published. This is the geometry that Wolf used in his publication. We are now, together with Wolf, doing again the problem, now using a new version of PenH with different nuclear interaction models. And this is the geometry that we are using, which is essentially the same than this one, slightly different from the one used by Goman and Sterpin. What I am showing you now is the numerical data of this plot, adding our results that we have just obtained. This is a work that we have in preparation. We have obtained this value that would go here in the plot. Again, not statistically compatible with previous results. And 150 MeV is not the worst case. At high energies, see which are the differences that you are obtaining. So, this slide, I wanted to entitle it, instead of ingredients of a Monte Carlo simulation, which is, I am recalling the previous slide that I showed you with the same title, Pitfalls of a Monte Carlo simulation, because all of these points are source of possible pitfalls or inadvertently introducing sources of bias. Primary source definition. Are we simulating a point source, a pencil beam? Do we need to use Fermi Ikes for simulate a realistic pencil beam, as we did in the case of the first results that I showed you of the pencil beam simulation? Geometry file. This is, in the case of the simulation of ionization chambers, this is a key issue. The geometrical description of ionization chambers is proprietary information of the manufacturer, and the information that we receive from the manufacturers is not always accurate. The definition of the material files, there are many variables here. Transport parameters, how do we define the simulation? Condensed or detailed? Variance reduction techniques, definition of tallies, all of these can be varied, and small variations on all these ingredients will produce substantial and noticeable variations in the simulation of dosimetry problems. As said, the simulation of dosimetry problems requires, is much more demanding in terms of accuracy than the simulation of dose distribution in patients. As I said, every step in the Monte Carlo simulation can become a pitfall. And what we need is more work in the field to improve the accuracy of interaction cross-sections, material-related quantities, radiation transport, and in order to improve the computation of dosimetry-related quantities. And very important, for the routine computation of out-of-field doses, all these improvements will be needed. And out-of-field doses is now a major issue when we are talking about the computation and the understanding of radiation-induced secondary cancers. Thank you.
Thank you so much. I'll do my solitary clap because everyone else is muted. Thank you, Lorenzo. That was really, really excellent. And I think you also provided a good background into how Monte Carlo works and what are the pitfalls. Because as we know with the computers, garbage in, garbage out. I have received a number of questions. Before I get to the questions, I'll start a bit more generically. Can I please ask you, what do you see the most exciting development in the proton or hadron therapy these days?
it's hard to say. Now there's a lot of hype in general about flash therapy, and I am getting a bit out of field. And this is very exciting, and a lot of people is being attracted. According to my understanding, I think that it is very important nowadays to further improve our knowledge on dosimetry, to link our dosimetrical knowledge with biological response. And this, I think, it is a very important subject area.
Fully agree.
To go into it.
Yeah, I agree that sometimes we get too technically and physics orientated and maybe overlook a bit the underlying biology. Yeah. So if everyone lets me, I will start with the questions from our audience. Dayananda from Chennai is asking, which Monte Carlo code do you recommend for the best accurate modeling in clinical proton beam energy?
Currently, I would say GN4 with a wrapper for specifically addressed for radiotherapy problems such as TOPAZ. That's what we use. Fluka also gives excellent results. And also there is also a wrapper called Flare. I am a user and let's say very closely related to the Penelope team, and of course I would like to tell you Penelope has arguably the best multiple scattering models in the market for electron transport or for charged particle transport, also for the electromagnetic part of protons. The result that we are seeing with PenH are very encouraging. However, in the case of Penelope, PenH, only protons are simulated. So if you want to take into account neutrons, then it is out of the game. So I would definitely go for JN4 with TOPAZ, alternatively for Fluka with Flare.
Okay, thank you. How do you see GPU as a solution for fast Monte Carlo simulation so that this can be used for routine treatment planning? This is coming from Sachin Dev.
This is an issue that some people, quite knowledgeable groups, I'm thinking, for instance, on the group of Steve Young in California, they have been recurrently trying to implement. The problem with Monte Carlo simulation of radiation transport is that ideally what you would like to do in a GPU is to distribute one primary particle per processor. So that if you have 500 processors, then you have 500 primary particles being simulated all at once. What happens is that since we are working with an stochastic approach and with random numbers, your first primary particle can have a type of interaction, a Compton, and your second particle can have another interaction, a Rayleigh or whatever, and all particles will have different types of interactions. And this is not good for the architecture of GPUs. GPUs are meant to do the same mathematical computations at once, all of them, with different inputs, but the same. So if one is doing a multiplication, to put it very simply, all others must do a multiplication at the same time. And the problem is not well suited for GPUs. The best results I have seen with GPUs is an increase factor of 10 to 70 at most, and obtaining that by reducing and simplifying a lot the physics. For a factor of 70, you do not do all the effort that you do modifying your code and implementing it into a GPU. Yeah. So what you do is you buy a more powerful computer.
Okay. Vasilius Boronikolas is asking, can we use GN algorithm for a pencil beam regarding the trajectory calculation of the beam and the depth deposition in the MR field, if you use, let's say, magnetic resonance imaging?
For magnetic resonance with proton therapy, or he means in general with?
I presume this would be with proton therapy.
With proton therapy, I haven't heard. Yes, there are some simulations of LINAC MRIs, this I know. Together with proton therapy, I have not seen. Mm-hmm. But yes, of course, you can. Most of the codes have the possibility to simulate coupled electromagnetic fields with the simulation of charged particles.
Yes. Sunil Sharma is asking whether the geometry of nozzle has also been considered in source term or geometry of your simulations.
No, in our simulations, not. What we have done is we have tallied, we have measured the fluence at the exit of the nozzle, and we have derived a virtual source based on the experimental measurements at the exit of the nozzle.
Mm-hmm. I have had a couple of questions about your last conclusion point about the out-of-field doses. Do you think that sometimes in the future it will be routine to calculate out-of-field doses for patients for risk estimation of second primary cancers?
I think we definitely should point into that direction, and this is something that we are working in. Actually, we are working in a European project called Harmonic, which is one of the objectives of the project. I mean, one must bear in mind that for out of field, far from the field doses, computation, accuracy is not that important. So mm-hmm. You do not need to get the dose with 1% accuracy.
Yes. So even if we have, you know, analytical models or some of those, that would be more than accurate enough.
For instance, yes, you can very fastly compute the dose analytically to a point, and then yes, use a GPU because you are using an analytical model to compute the dose distribution far from the field.
Yeah,
at several points.
Yeah. Few people have asking about comparison of whether GATE is suitable for simulation of hadron therapy or whether Primo can be used for proton dose calculations. Do you have any comments?
GATE, for sure, yes. GATE is another wrapper like Topaz. I do not have experience with GATE, but what I've read is, yes, it is possible. At the end, your computation engine is GN4. Primo, no, nowadays not. It is one of our objectives to implement this new version of Penelope for protons into Primo and eventually produce a Primo for protons. But this is, let's say, in the long term. It requires a lot of work and not certainly before 2 or 3 years.
There is a question from Arif about the dose contamination from a secondary fragmentation. Do you have any comments? I don't think whether this is very important in proton therapy, more in hadron.
More in hadron, yes, not in proton therapy.
So we don't have to worry about it. Would you use Monte Carlo? Meyer is asking to develop shielding, calculate shielding for proton therapy.
Yeah, that's relatively easy, and this is one of the fields in which MCNP is very much used. Many people doing simulations of shielding, they use MCNP, but you could use also GM4 or whatever. Yes.
Mm-hmm. Meyer is also asking, what would be accuracy of ray station Monte Carlo in the presence of high Z materials, if you are familiar?
We could not do that because ray station is a black box. So
yes.
We can introduce some materials. You see, for instance, we simulated lucite, but we were not able to simulate brass or aluminum. In any case, it is, even though you could implement it, the code is not designed for that.
Mm-hmm.
The code is designed to compute accurate and fast dose distributions in patients, and that it does very well.
Well, yeah. Now, Gagan Preet is asking, what do you say about deep learning algorithm for mimicking Monte Carlo dose calculations in a treatment planning system? These questions are becoming trickier and trickier, I tell you.
No idea, no experience I have.
But perhaps that would be a challenge for our younger physicists up and coming to resolve in the future.
What some people is doing in, let's say, going into this direction is using artificial intelligence for finding initial beam parameters that represent, that can model your source. Instead of going through trial and error to using artificial intelligence or neural networks, these are some approaches that people is now starting, and there are some very interesting recent works in that direction.
Mm-hmm. Hidea is asking, can you give us a good example of improving simulation efficiency?
There are many ways, and that depends mainly on your problem. A very simple, I do not know if it's good, but a simple example. In the case that I showed you, that we were simulating a pencil beam impinging on a water phantom. In order to improve simulation efficiency, our tally, instead of using parallelepiped voxels, that is cubic voxels to tally the dose, we use voxels with this, or bins with the shape of polar coordinates, of cylindrical coordinates, so cylindrical. So we had cylindrical shells, and then we exploit the symmetry of the problem. So this is the typical example in which you can exploit the symmetry of the problem in order to improve the efficiency of the simulation.
Okay, John, if you allow me, I will do one or two more questions, and
sure,
then we'll
go ahead. Go ahead,
yes.
Eva.
Andrzej Kacperek is asking, what benchmarking do you do against actual experimental measurements?
I do not understand it. We compare our simulated results with the experiments.
Experimental measurements, as was shown in your lecture.
That's what we did. Yeah.
Yes, yeah. Is there a free version of MCNP for a student?
MCNP, I think it is free. Let's say the hurdle is that you need to ask it. I do not remember, but it's a U.S. institution, and then they decide if you can receive it or not. Depending on the country, they have a policy, and some countries are not selected.
Mm-hmm. Right. So it's worth trying. Another young physicist is asking, we would like to learn GN4. Would you recommend any website or learning sources for a beginner?
I would go to the source of JN4, start reading the manual. There are courses of JN4. JN4, it's in general, all Monte Carlo codes are not easy. And I mean, you can, let's say, relatively fast download the code and get a simulation running, but to understand what you are doing and to understand the results that you are obtaining, I would suggest either to attend a course or to go into, deeply into the manuals. So it requires time. There are JN4 courses that more or less once a year they are run. So I would suggest to go to one of these courses.
Mm-hmm. I will finish with the last lecture. Is there a difference in Monte Carlo code performance if the Monte Carlo is written in different programming languages?
Sure, of course. But that depends not on the Monte Carlo code, but depends on the language. Still, the fastest language for mathematical computations is still Fortran.
I love Fortran.
Welcome. I'm glad that you say that. Me too. Penelope is written in Fortran. Then you have codes written in C++, which is the case of JN4. JN4 is, C++ is also very fast, nearly as fast as Fortran. But the speed of the simulation, the inherent speed of the simulation of the code depends mainly I would not say whether you choose Fortran or C++, but on the physics that you implement.
Yeah.
And how you implement that physics.
And
For Penelope is not particularly fast. Penelope has a very accurate physics, but it is, as you compare it with EGS, for example, it is very slow compared to EGS.
Well, it sort of would then depend how people set their input parameters. And whether they are logically set up.
And then it depends on the compiler that you use. So in the case of Fortran, which is the one that I know the best, you can use GFortran, which is free, or you can use Intel Fortran, which is commercial, but you get simulations that run from a factor to 2 to 3 faster. So if you are talking about an hour, it doesn't matter. If you are talking about a month, it's not the same waiting 3 months than waiting 1 month.
Yeah. Lorenzo, can I please ask you to stop sharing? And I will now...
Oh, sorry. Yes.
Yeah?
I remained here.
That's perfect. It should be somewhere at the top.
Yeah.
Thank you. So I think we have run out of time, but I'm very pleased because we had large amount of questions. If you have time, you can go through all the beautiful comments left for you by the participants about how they enjoyed your lecture. And John, would you be able to let us know when the lecture will be uploaded, or Magdalena? There have been a number of questions about that.
Very soon. By the way, I'd like to thank Magdalena, Professor Stoeva. She is responsible for all technical aspects and recording. And this
did a great job.
Great job. This means that the webinar will be available on our website, on IOMP's website very soon. Tomorrow, I guess. So it's a matter of hours or 1 day. Lorenzo, unbelievable. Excellent talk. Thank you. Messages. I'm reading messages. Excellent talk. Many thanks for your valuable lecture. Excellent, very insightful, nice, clear, delivery. Sorry. Can you arrange another lecture on Primo? Another. So
that depends on you.
So lots of nice messages, but time is very limited, unfortunately. Thank you, Eva. Thank you, Lorenzo. Thank you, Lorenzo, for your great presentation. It was an excellent webinar, and I'd like to also thank our colleagues for their active participation. Tomorrow, same time, another webinar. So this topic, the topic will be, it's a very interesting topic. Management of radiotherapy patients with implanted cardiac devices. So, see you soon.
Thank you.
Thank you, everyone. Good
Bye.
night.
Thank you, everyone.
Thank you, everyone. Thank you.